Okay, so after substitution, the next thing was definite integrals that we talked about. And really the only thing you had to be careful about here was that when you make your substitution, it does affect the bounds. So at this point, you should be starting to get fairly confident with your substitution choices. So I'm not going to spend a ton of time going over these strategies here. But the best candidate here is to substitute for x squared minus 8, which means now my upper bound is going to change. Instead of being 3 as my lower, it's now going to be 3 squared minus 8, which is 1. And my lower bound, which is going to be 6 squared minus 8, which is 28. So I also have to change the bounds when I rewrite my integral. And of course, du will be 2x dx. So there's all the pieces that I would put into this. I would have 1/2 the integral from 1 to 28 of du over root u, u, and there's still a 3 that's there. So at this point I could use the power rule in order to figure out what this integral would give me for an antiderivative. So that exponent is -1/2. One higher will be at 1/2. So if I simplify this a little bit, I'd get 1/3 square root of u evaluated from 1 to 28. So that means I'd have 1/3 root 28, take away 1/3 root 1. Okay, so I won't take your time putting it in the calculator, but that's about what it should have looked like when we did a definite integral. So I'm going to have you try the second one on your own, and again, remember, make your substitution, but you also need to change your bounds when you do that. So a good choice for substitution in this example would be x plus 1. That means where my bounds are going to change. The lower bound is going to be 0, and the upper bound is going to be 1. And in this situation, dx is equal to du. I also, I'm going to have an x left over, so I'm going to need to figure out here x is equal to u minus 1. So that way when I end up in this situation, I can replace that x squared with u minus 1. Oops. Okay, so if I expand that out, that's probably the easiest way to go, is just, it's only squared, so it should be fairly easy for you to write this out. Minus 2u plus 1 root u du. And then if I just expand that out as one more time, I'll have u to the 5/2 minus 2u to the 3/2 plus u to the 1/2. And I can use power rule at this point to finish off that integral. So if I used power rule, I would end up with 2 out of 7 u to the 7/2. Take away 4 out of 5 u to the 5/2. And we'll add 2/3 u to the 3/2. And we're evaluating this one from 0 to 1. So again, I could probably come up with a fairly quick, let's see, it would be 2 out of 7 minus 4 out of 5 plus 2 out of 3. And at 0, there'd be nothing there. So we could work that out to get the exact value for that area. So any questions that relate to definite integrals? Can I just see, show of hands if you were able to do that last question on your own there? Okay, good. So the next topic that we went on to from substitution was numeric integration for antiderivatives, which you may not know a technique for. There is a technique for this one here. It is possible, but you don't know the technique. It's the same technique that I showed you guys for the natural logs antiderivative. Do you remember what that one was? Yeah, it's thinking about the product rule in reverse. It is possible to find this antiderivative if we did things that way. But anyways, beyond our course, we're not working up to it, but those of you who will be taking Calculus BC, you may want to fool around with that one and the product rule going backwards. But for us, we're only expected to do it numerically. So what I'm going to do is we'll just review what those formulas look like. So some things that were factored out. The top of this fraction, before I start, what's on the top of this fraction? Yeah, the width of this integral. So b minus a is pi. We factored out each one of them is going to be, if I have a width of pi, and I have 4 trapezoids in this case, that means I can factor out a pi over 4 for each of them. That'll be the width for each trapezoid. So that's what gets factored out here, pi over 4. There is another number, however, that goes in there. So do you remember what else was in there? A 2, yeah, on the bottom. Why is there a 2 for the trapezoid rule that's factored out? Yeah, there was a whole bunch of halves, and we factored out the 2 from there. The way that I remember that there's a 2 on the bottom is trapezoid rule is making lines. So if I'm making lines like this, I need 2 points in order to make a line. So that's how I remember trapezoid rule has a 2 on the bottom. Okay. Inside the brackets now, the first point for any of the trapezoid rule and the last point in the trapezoid rule, they only happen one time. But any point in the middle, how many times will it happen? Good. That's because in this rectangle here, that point is the right side. But in this rectangle, that's going to be the left side. So it's actually been used twice. That's how I remember that there's going to be a multiplication of 2 on everybody else. So if each trapezoid has width pi over 4, that's what I'm going to move up by. Starting at 0, and I move up by pi over 4 with each step in this calculation. So the next one, this would be pi over 2, but just so you can see the pattern, I'll write it out the long way. And now where were we at here? That's 3 pi over 4 cosine 3 pi over 4 and pi cosine of pi. So that would be enough for us to do it in the calculator. And again, today I won't take your time up to do that, but this would be set up for trapezoid rule. Okay? So now we will take a look at Simpsons Rule. So I'm going to erase my little picture down here. Okay, and I'm not sure if everybody's, maybe I should just say that one more time here. If we've got a width of pi and I'm using 4 trapezoids, that's how I know how far I'm stepping along, okay? So that's why I went from 0 to pi over 4, and then from pi over 4 to 2 pi over 4, and then from 2 pi over 4 to 3 pi over 4, and then on to pi. So here, let's talk about Simpsons Rule. We're going to end up factoring out that pi again over 4, because even though it's not a trapezoid anymore, remember Simpsons Rule, what's the difference between Simpsons Rule and the trapezoid rule? It's a curve, right? What kind of curve was it? It was a parabola. Yeah, that's what he used. So roughly, you're going to have something that might look like, that's not a very good curve. Let's try that again. You might have something that kind of comes together like that. You still have the same, it's sort of a rectangle, so you're still going to be factoring out that pi over 4 for the width of each one of them, right? Now, the way I remember that there's a 3 in front here is a line needs 2 points, a parabola needs 3. So this is going to end up factoring out a 3 on the bottom here. And the pattern, do you remember how the pattern went in Simpsons Rule? 4, 2, 4, 2, 4, 2, right. So it's going to be very similar to what we had. 0, cosine 0, start with 4. So the coefficients are going to change. But remember, the amount of operations we're doing is the same, but we get all that more accuracy this time. This would be a better approximation than the trapezoid rule, and I get a better approximation without having to do any extra work. So let's see here. So that would be the trapezoid rule for the same question. Sorry, thank you. That would be Simpsons Rule. Yeah, that's right. And remember, as far as our course goes, part of our local curriculum is that we do both Simpsons Rule and the trapezoid rule. But the AP curriculum is only asking about trapezoid rule. So after we finish this discussion, we'll focus on trapezoid rule from here on out. Okay. From here, we talked about 2 other topics, which were using natural logs and antiderivatives for inverse trig. So let's start with natural log. Well, I'll ask you, the other class, they needed a little bit of a hint to get started. Can you think of how to get started on this? Well, we may end up doing substitution, but again, we need to see the derivative in there. And I don't really see, like, the derivative for square root of x. It's not in there, right? It's not quite what I'm... Yeah. Yeah, that's the way to do it, right? I could rewrite this as 1/2 natural log x over x. So really, the integral I'm looking at would look like this. Natural log x over x. Yeah, so remember those log laws? Usually when you see a logarithm, that's one of the things, remember we did that little bit on log differentiation? You usually want to get rid of all that nasty square roots and all that extra stuff. Separate them if you can. You'll have less pieces to work with. So this time, I'd recommend you look at the 2 pieces like this. Some of you might not need to, but this is what I recommend you think about the 2 pieces. So what do you think? What technique would you use here? Yeah, how come?
Because mine accepts that if you derive every one of x.
Say that one more time.
U as line x, and then
Oh, okay.
derive it of v1 over x.
Yeah, that's right. So you can see a function and its derivative. So if we made this substitution, then we'll be able to rewrite this integral as u du, which is u squared over 4 plus a constant, and our substitution was the natural log x, so this would be my final answer. Okay, how about the next one? Does that one look ready to start anything, or anybody recognize a technique that might work? Yeah, help us out. You want to put a 2 in the front? Okay, so you want to balance it like this? Well, you're absolutely correct. I don't know if everybody knows why you did that. Anybody tell us why Jackie decided to do that? Sure, Jonathan?
Because the 2x is the function with the
You're close. You want to help him out?
Because the derivative of e to the 2x is 2e to x.
Yeah, so this piece, if you make this whole thing your function, then this here would be my derivative. So my substitutions could go e to the 2x plus 1, and du would be 2e to the 2x. Remember, there's a chain rule in there because it's not e to the x, it's e to the 2x. That's where the extra 2 comes from. So that means I'm ready to make my replacement since we already put the 2 in the half to balance things out. So this would be 1/2 the integral of du over u. And any ideas? How would we integrate that? Ooh, I heard a few suggestions. What's the exponent on this? If we were to try power rule, will it work?
No,
How come it doesn't work?
it goes to 0.
Yeah, so we can't, this won't make sense, right? Be careful, this doesn't make sense to do that, right? So that's how we know we got to move to the logarithm. That should remind you that's not possible to do, so let's get rid of it. And let's make this 1/2 the natural log of u. So for us it was 1/2 the natural log of e to the 2x plus 1. And there's no way that I'm going to get a negative out of this value, so I could just write it as 1/2 the natural log e to the 2x plus 1 and a constant. So the absolute value brackets aren't needed. Okay, so the last couple of questions that we'll give it a try with was just recognizing your inverse trig antiderivatives. So for the first one, what do you think? How could you match the first one up to an antiderivative? How come? No square root, right? That was the pattern we were looking for. Is we had a couple of squares, so one of the values is 4, the other value is x. If I check this, do I need to go through a full proper substitution? No, I don't. There's no constant that's been introduced here. So because it's directly related, du equals to dx, I can just go and find my answer here. And the pattern was 1/4 arctangent of x over 4 plus a constant. Now remember, this wasn't the case for us, but if we would have gotten something like du equals 3 dx, then we would have need to do a proper substitution on that one to make sure that we got the right constants in front. Otherwise, you might have been off when you got your answer. Like you might have had, in this case, it might have been like a 1/12 or something different. There might have been a different constant instead of a 1/4. Okay, so watch out for that when you do your inverse trig. Now, what about the next one? Anybody think of how the next one might work? That's very smart. Okay. How did you see the power rule so easily?
the function and its derivative.
Okay, so here's, for the rest of us who are probably wondering how the heck John figured that out, if we were to go like this and just say, tell me about it, if the derivative looked like that, what would you be guessing? What kind of antiderivative do we have? Arc sine. So you're in your head, you might be thinking, okay, I have an arc sine antiderivative, but I also have an arc sine. Uh-oh. So what am I supposed to do? Well, you might be overthinking it. This here would make a great function, and this here would make a real good derivative, right? So if I rewrote it, 1 over root 1 minus x squared times arc sine x. That's the function, that's the derivative, So yeah, it works nicely for doing power rule. We could do a substitution in it, which I would suggest that for us, that's what we do just to get good practice working with that technique. So I'll go and finish it off using substitution. For example, I'm going to make that my function. So du would be equal to 1 over square root 1 minus x squared dx. So then I can make my my change in the integral here. It'll be u du, which would be u squared over 2 plus a constant. And for us, u squared was the arc sine. So it would be arc sine x squared over 2 plus a constant. Okay. Okay, so that takes us to the end of integration. And that homework up there is accurate, so you guys can get started on it right now.